In this video, we'll understand vector embeddings in a simple way, see how meaning can be represented as numbers, and then walk through how semantic search works step by step. After that, we'll look at a practical Python implementation using embeddings, FAISS, and retrieval-based question answering. We'll also pause for a few quick quizzes so you can check your understanding as we go. A vector embedding is basically a way to convert data like text, images, or audio into numbers. But not just any random numbers. These numbers are arranged as a high-dimensional vector, and that vector tries to capture the semantic meaning of the original data. So instead of storing only words or pixels directly, AI systems work with numerical representations that help them compare meaning, similarity, and relationships more effectively. To understand embeddings, first imagine a vector space where each word is placed as a point or arrow from a central origin. In the example, terms like man, woman, boy, girl, old, infant, and child are arranged to show semantic relationships. Opposite directions can suggest contrasting ideas, while nearby positions can suggest related meanings. This is a simplified picture, of course, because real embeddings use many more dimensions, but it gives us a solid intuition. The visual example is useful, but real-world embeddings are much richer. They do not depend on just one or two dimensions like age or gender. Instead, they capture many subtle patterns in language or other data. That is why embeddings can help systems understand that two different phrases may mean nearly the same thing, even if they do not share the same keywords. This is one of the biggest reasons semantic systems are so useful. Vector embeddings are used across modern AI. In semantic search, both the user query and documents are converted into vectors, so the system can search by meaning. In natural language processing, embeddings help models understand context and relationships between words or sentences. In LLM-based applications like ChatGPT with retrieval augmented generation, embeddings help fetch relevant knowledge. And in multimodal AI, models like CLEP can place text and images into a shared embedding space. Now that we've covered embedding basics, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. What does a vector embedding mainly do? The correct answer is converts data into semantic numerical vectors. A vector embedding converts data such as text, images, or audio into numerical vectors that capture meaning. Question 2. In a simplified vector space, what often suggests similar meaning? The correct answer is closer distance between points. In vector spaces, nearby points usually indicate stronger semantic similarity. Question 3. Which is a common use of vector embeddings? The correct answer is semantic search. Semantic search is one of the most important applications of vector embeddings. Now let's move to the workflow. First, we load the required code modules for embeddings and vector search. Next, we load the source data, which can be text, images, or audio. For text-based retrieval, the content may come from documents, sentences, or paragraphs. Then we split large content into smaller chunks. This step is very important because embedding models and language models have token limits, and smaller chunks also improve retrieval quality. After chunking, we create an embedding model instance, such as OpenAI embeddings. This model converts each chunk into a high-dimensional vector. Once the vectors are created, we store them in a vector database or vector store, like FAISS, Chroma, or Pinecone. This storage layer is what makes fast similarity search possible later. So at this point, your original content has been transformed into searchable meaning-based representations. When a user asks a question, that query is also converted into a vector. The system then compares the query vector with stored document vectors using similarity measures such as cosine similarity or Euclidean distance. The most similar vectors, often called nearest neighbors, are returned. This is why semantic search can find relevant results even when the exact words in the query do not match the document text. Now that we've covered search workflow, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. Why do we split large documents into chunks? The correct answer is because models have token limits. Chunking is essential because embedding and language models cannot process unlimited text at once. Question 2. Which tool mentioned in the article is a vector store? The correct answer is FAISS. FAISS is commonly used to store and search vector embeddings efficiently. Question 3. What happens to the user query in semantic search? The correct answer is it is converted into a vector. The query must also be embedded so it can be compared with stored vectors. In the practical implementation, we first prepare a custom text file as the data source. Then we create a Python file, for example vector.py, though the name can be anything. After that, we install the required Python modules. The script loads the document, splits it into chunks, generates embeddings using OpenAI, and stores those embeddings inside a FAISS vector store for semantic retrieval. Once the FAISS index is created, we can connect it to a retrieval QA chain. This setup retrieves the most relevant chunks first and then uses a language model to generate the final answer. A nice advantage here is that you do not need to recreate embeddings every time. You can load the earlier saved FAISS vector store, such as a folder named face_index, and continue asking questions on top of the already indexed content. When you execute the script from the command prompt using a command like pyvector.py, the system processes the data and can answer queries from the indexed content. The output shows the response generated through retrieval and the language model. If you no longer need the vector stored, you can delete the FAISS directory completely. That removes the stored index files from the file system and clears the saved vector database. Now that we've covered implementation steps, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. What is the role of retrieval QA in this implementation? The correct answer is retrieve relevant chunks and generate answers. Retrieval QA first fetches relevant document chunks and then uses an LLM to answer the question. Question 2. What is the saved FAISS folder name mentioned in the article? The correct answer is face_index. The article specifically mentions a saved vector store named face_index. Question 3. How can you remove the vector store? The correct answer is delete the FAISS directory. Deleting the FAISS directory removes the vector store and its stored index files. That's it for this lesson. If you understood how embeddings, semantic search, and FAISS-based retrieval fit together, you've already covered a very important foundation of modern AI applications. Keep exploring, try building a small project of your own, and I'll see you in the next video.